Okay, so let me share my screen. Okay, can anyone confirm that screen is visible?
Yes, sir.
Okay, thank you. Okay, so good afternoon. Now I think we have covered many things, and we were looking at block cipher, especially iterated block cipher. And today I'm going to look at one very interesting thing, digital encryption standards, which was very famous at one point of time, and still it is of course famous, but now it is replaced with AES, Advanced Encryption Standard. So we'll talk about Advanced Encryption Standard in my next class. So today I'm going to give you a little bit of history about DES, Data Encryption Standards, and how it works. Especially I'll give an example, the key idea about it. So what we are doing here, we are still looking at private key crypto system. So 1 minute, let me. Yeah, so we were looking at this private key cryptology or symmetric cryptography. So block cipher is a iterated cipher, as I told you, and so it has certain round functions. And using one key, we generate a key schedule to do encoding. So this is our X is our plain text, and Y is our cipher text with so many rounds of functions. As you can see. So from here to here, 1 minute. So from here to here, we have all these functions, right? With round functions we are using. So now, data encryption standard. Actually, it is based on a network known as Fistel network. Okay, so this was kind of invented in 1973. Okay, so it's interesting thing. So several block ciphers are based on this. I should mention that several block ciphers are based on this structure. Okay, so what is a Fistel network? In this fiscal network, the block size is n is equal to 2w. Okay, number of rounds, suppose I'm calling it as d. Number of rounds, there are d rounds, certain number of rounds, and so for each round there is a round function. So we have d round functions, f1, f2, I can call it as fd, from a bit of for binary string of length w, to give you binary string of length w. Okay, so where it is used, it is used in DES, which we are going to tell what is DES. Idea, this is also a block cipher. RC5, that's another block cipher. Reverse cipher number 5, actually it is pronounced as reversed cipher number 5, and many other. But of course I should mention that it is not used in AES. Okay, advanced encryption standard is not based on Fistel network, so that is a little bit different. So let me show you. Here is an example of Fistel network. So f1, f2, this is fd actually. Yeah, f1, f2, fd. So these are the functions. So left, right, L1 is equal R0, R1 is equal to A0 exclusive for f1 of R0. So basically there are certain bits which are incoming. You divide into half part, left part, right part, and then you do these kind of functions you allow. So do these kind of operations. So L2 is equal to R1, R2 is equal to L1 exclusive for F2 of R1, and so on. This is how you do the encryption, and this is how you do the decryption. So this is pretty standard, and these are the round functions F1, F2, Fd. This is a general framework for Fistel network. Okay. So now let me talk about something about NIST. It stands for National Institute of Standards and Technology. Okay. Formerly, it was known as NBS, National Bureau of Standard, you can call it. So it's a non-regulatory federal agency. Okay. So it's develops standards and technology in US. Okay. Cryptographic standards and applications. And also it maintains federal information processing standards known as FIPS. FIPS. So this defines security standards. So our next cipher DES was mentioned first time in FIPS. Let me give you a brief history of DES. Okay. In 1967, pistol was invented at IBM. Okay. And the initial cipher based on this was Lucifer. Block size 128 and key size 128 bits. So block size 128 bits, key size 128 bits. Then in 1972, NBS, National Bureau of Standards, asked for an encryption standard. So this NIST now asks for standards to be made for the next generation cryptography. For example, recently they've asked for post-quantum crypto systems, that in the era of quantum computers, what kind of standards we should follow. And they are working on so they are working on code-based cryptography and lattice-based cryptography. Anyway, in 1975, IBM developed DES. It was a kind of modification of Lucifer that they developed. So here the block size 64 bits, key size 56 bits. Okay, 1975. National Security Agency of US suggests modifications into it. And finally, in 1977, NBS adopts DES as encryption standard. In FIPS, as I mentioned, 46.1, 46.2. This original document is now available. You can download and see yourself actually. Finally, actually in 2001, NIST adopts Rajendel as replacement to DES. So this was advanced encryption standard. So I am going to talk about that also in my next class. So this is a brief history of DES. So let me So what are the DES features? So let me show you. Block size 64 bits. Key size 56 bits. In reality, it is 64 bits only. 8 bits are for pair T check bits. For error control. So normally, that means for 7 bits, if there are total 64 bits, so you can divide it into 8, right? 8 bits one group, and the 8th bit is nothing but exclusive OR of the previous 7 bits actually. That is how it works. Number of rounds is equal to 16, and we have 16 intermediate keys, each 48 bits. Okay, so we have something like DES here, plain text, then we have ciphertext, and here is a key. 56 bits, plain text 64 bits, and ciphertext 64 bits. So as I mentioned, this key is 56 bit, but actually the 8 bits are extra. So there is a block of every 7 bit. After 7 bit, there is one extra bit, which is parity check bit. So total are 64 bit here also. So let me show you how it is there. Something like this. We have 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 8. Something like this. So we have 1, 2, 3, 4, 5, 6, 7, 8. This is 57, 58, 59, 60, 61, 62, 63, 64. So these are 7 bits here. These are 7 bits here, which are data bits. 7 bits, This bit and this bit is parity check bits. So every 8 bit. So for example, 8 bit. So next will be after 16 bit will be parity check bit and so on up till 64, right? So these are exclusive are of previous 7 bits. Normally we take this kind of parity. Okay, so this is how key is there. I'll show you how to generate a key. It's bit lengthy process. So here is in general DS rounds. There is the initial permutation. 64 bit is going in, as you can see here. Initial permutation round, key 1, permuted choice, left circular. So what are these things? I'll show you in details. Okay. And then we have this round, so basically this portion is for keys. As you can see that for generation of the keys, 16 keys are here. And then we have round 16, the inverse initial permutation, and the ciphertext is coming here. So input is here, output is here. So let me show you. So here is the input, initial permutation. Then you break into two parts, left portion, right portion. Okay. And then there is this function, then key, L1, and then we have this kind of thing. There are 16 round functions. Pre-output, I will tell you what here you have to actually again change it, an inverse initial permutation, and then there is a output. Now actually, what are the details here? So initial permutation of plain text is L0 R0. Then we have Li is equal to Ri minus 1. Okay, you can see from here Li is equal to Ri minus 1, right? Then Ri is equal to Li minus 1 exclusive for function of Ri minus 1 comma Ki. Ki's are the keys. Okay, and then Y is finally IP inverse R16 L16. Now these functions here, these functions that we are using here, functions like 32 bits cross 0 1 48 bits goes into 0 1 32 bits. So I'll explain in details about these functions. So these LIs, so basically LIs are 32 bits and RIs are also 32 bits. So these are 32 bits. The total 64 bits. Okay. And then there is this key schedule K1, K2, K16. Okay, 48 bit round keys. That are derived from 56 bit key, master key. So what is the mechanism for generating master key? I will show you. So this is a general general scenario. Let us look at the picture now. So input 64 bit initial permutation. I will explain what is initial permutation. L0 R0 32 32. Then this is a function which is acting on it. Okay. This is a typical scenario of the function in one round of DES encryption. Okay. And one R1, and like this it continues. Here is the initial permutation. So you see 58 50. So it is written in the matrix form, but you can read it row wise. Okay. The first bit of the output, so basically is taken from the 58 bit of the input. First bit of the output is taken from the 58 bit of the input. The second bit from the 58th bit, and so on, with the last bit of the output taken from the 7th bit of the input. Like this you permute. Okay. So this is how the initial permutation that is happening here. This initial permutation we are talking about. Initial is 64-bit, then you apply the 64-bit permutation, and then you divide it into two halves, left half, right half, and we call it L0 R0. Then you do this kind of calculations. Okay, so now DES rounds, as I mentioned, IP of x is equal to L0 R0, Li is equal to Ri minus 1, Ri is equal to Li minus 1, x is equal to this function, and y is equal to this R16 L16. As you can see that here, it should come as L16, but then we switch the pre-output here. Normally R16 is this and L16 is this, right? So they are switched in the pre-output, and then we apply the inverse permutation, IP inverse, to the 64-bit output. So this is the general scenario. 16 rounds of functions are there, round functions are used. So what are these functions? Let me go into details of these functions. So this is the final permutation, inverse permutation. Again, reading in the same fashion. Bit 40 of the pre-output block as its first bit. Okay, bit 8 is as a second bit, and so on. Finally, bit 25 of the pre-output block is the last bit of the output. We apply this inverse permutation. Okay. So in a typical DS round I, you see that 32 bits are coming here, 32 bits are coming here, and then 32 bits are out, 32 bits are out. There is a function. Ki is 48 bit, which is mixing, taking Ri minus 1, Ki, and then giving you Ri, right? This formula. So what is this function here? That is something we are really interested in. So let us see this in little bit more details. So basically, this function is, first of all, as you can see here, f is taking 32 bit here, right? And now it has to mix with 48 bits. So how that is possible? 32 bit, how will you mix with 48 bits? So we need some sort of expansion function here. Here is the expansion function here, okay, which is expanding it, then it is mixing, and then we are getting these BIs. Then we are using S boxes. These are eight X boxes, substitutions. Then we are getting these 8 bits, eight outputs here. Okay, so each one is 4 bits long here, and these are 6 bits long. So let me show you how these things works. So we have Ri minus 1 is 32 bit. There is expansion function here, E expansion function. So convert it into 48 bits so that it can mix with a key of 48 bits. So what is expansion function is, you can see here, 32 is repeated twice, 32 here, 32 here. 1 is repeated twice here, here. 2 is not repeated. 3 is not repeated. 4 is repeated twice. You can see here, here. 6 is not repeated. 7 is not repeated. 8 and 9 is repeated twice. Okay. Then 10, 11, nothing. 12, 13 is repeated twice. 14, 15, nothing. 16, 17 is repeated twice. 18, 19 is not, we are not doing anything. 20, 21 is repeated twice. 22, 23, we are not doing anything. 24, 25 is repeated twice. 26, 27, we are not doing anything. 28, 29 is repeated twice. Okay, so there are 16 bits which appear twice in the expansion function. So basically what we are happening, this function takes a block of 32 bits as an input and produces block of 48 bits like this as output. So we take 32 bits, repeat it twice, 16 bits are repeated. So we get 32 plus 16 is equal to 48 bits. Any question at this point? I think this is something interesting. So you look at the expansion function, taking 32 bits and then producing 48 bits. Okay. Now these 48 bits, now we have to mix with key. Okay, 48 bits key, and there is a exclusive OR. Some output is coming here. Now you can see that there are 8 blocks here. We can divide these 48 bits into 8 blocks, 6 bits each. So 6 here, 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 6 here. So 8 into 6, 48 bits, right? Now we are using S boxes. S boxes are pretty interesting thing here. Their input is 6 bit, S boxes output is 4 bits. 4 bit here, 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 4 bit here. Okay, so how these S boxes are working, and then once we have these 4 bits here, we are combining it, we are getting 32 bits. Then we again apply a fixed permutation function, P. I'll tell you what is this P here. So but before that, first let us look at what are these SIs, S boxes. So these 8 S boxes, they are kind of 4 by 16 matrices, you know. So these are the only nonlinear elements in the DS design. Each S box takes 6 bits as a input, 4 bit as a output. Okay, 6 bit as a input, 4 bit as a output for each of these 8 S boxes. So each S is a matrix 4 by 16 with values from 0 to 15. Okay, and so here is one example. See, this is 0 to 15, 0 to 15, 0 to 15, 0 to 15. In some fashion, they are permuted, you know. Okay, now what? B, so how do this function works? B is a 6-bit long, so suppose it is B1, B2, B3, B4, B5, B6, right? Now, what we do, we look at this BIs, okay, and then look at the first bit and the last bit. The first bit, last bit is a binary thing, convert into decimal, and that is the row number, row of the matrix, that is R. Okay, and then B2, B3, B4, B5 is a binary, convert into decimal, it is nothing but the column of the matrix. Okay, this is 4 by 16 matrix. So then you look at that particular row and particular column, whatever is the representation is, so of the a typical matrix element is SRC. So whatever matrix element is there from 0 to 15, look at its binary representation, and that is nothing but 4-bit long C as a output. Got it? So let me give you an example here. Suppose B as a input is coming 1, 2, 3, 4, 5, 6 bit. 6 bits are coming. Okay. You look at first and the last, which is 1, 1. B1, B6 is 1, 1. 1, 1 in decimal is row 3. Okay, so I have marked row 3 here. Then look at middle bits 0, 1, 1, 1, which is 0, 1, 1, B2, B3, B4, B5, which is 0, 1, 1, 1 is column. So decimal it is 7 actually. It is column here 7. So 3 and 7, the element is 7 in the matrix. So that means S3 is 7 is equal to 7. The binary expansion of 7 is 0, 1, 1. So the output is 0, 1, 1. So basically the function which is acting on capital B giving you C, right? This is 6 bit and output is 4 bits. Okay, let us look at another example. If B is 0, 1, 1, 0, 1, 1, what is C? Look at 0 and 1. 0, 1 is 1. 0, 1 is 1 and 1, 1, 0, 1 is 13. So 1, 13, first row 13 column. First row 13 column, you know. We have 5 here. You can see that this 5 is there. So that means S1 13 is 5. Binary expansion is 0, 1, 0, 1. So this is how, you know, these 6 bits will convert into 4 bit. Any question at this point for these S boxes matrix. Any question? Any question? Okay, so now I think you understand what is going on in terms of these S boxes. So basically we have got 4 bits as a output, and these are 32 bits. Now we apply a fixed permutation. So I will show you what are these matrices, all these 8 matrices. For a long time it was a mysterious thing. People used to say that I don't know why these S matrices are, these S boxes matrices are coming. Maybe there is a trapdoor so that US government can spy on anything, why these are the fixed matrices. But anyway, these are the all matrices. I have shown you S1, then S1, S2, S3, S4. Okay, then we have S5, S5, S6, S7, S8. All these 8 matrices were used. These are the standard. Okay, and the primitive function P is this. On 32 bits, you need to apply a primitive function, right? So this is that function that you can apply here. This function I am talking about. This function P. Okay, so this P is fixed. These S boxes are fixed. Okay, and then we see the thing. I have not told you how to generate the key. So let me show you the key thing part also. So key generation is also a bit tedious process, but anyway, what you do, 64-bit key. So actually it's including parity check bits, right? As I mentioned, otherwise it is 58 bits master key. Okay, then what you do, so if you look at only 28 bits, C not, so we knew first we apply permuted choice 1 matrix. So this is 1 matrix and permuted choice 2 matrix. This you need to apply. So permuted choice 1 matrix is this one. Okay, this one. Okay, left and right, and this is permuted choice 2 matrix. Okay, so you can see that parity check bits, namely 8, 16, 4, 32, 40, 48, 56, 64 are not chosen. They do not appear in PC1. We only apply to non-parity bits. Okay, so then we have this C0, D0, then we left shift, we are doing some shift operation. So what are these shift operation? Ci is equal to lsi ci minus 1, di is equal to lsi di minus 1, and ki is equal to pc2 ci di. ls left shift operations only shift one position if I is equal to 1, 2, 9, 16. 1, 2, 1. So basically 1, 2, 9 or 16. When I is equal to this, then only apply left shift one position, otherwise shift 2 operations. Okay, okay, this is the thing. And then permuted choice you have to use to get K1, the first key, K1, then K2, and so on. You get K16 in general, 48 bits as a output. Okay, so let me now give you a specific example, very specific example how this is going to work. So here is a working example. Suppose the plain text is this 16 decimal thing. So you can see here, this is our plain text message. Okay, I mean hexadecimal order. Okay, so you can see that how many of them are there? 10 and 16 bits are there, right? Writing M into binary format, we get 64-bit block. This is capital M. Then you divide it into 2 parts, left part and right part. Okay, so 32 bits each. This is 64 bits. This is 32 bits, left and right. Now suppose the key is a hexadecimal key, the master key is like this. This gives us a binary key. The binary expansion is something like this. This is our master key. Okay, remember, so grouping them in 8 bits together, of which last one in each group is unused. So this key is unused, this key is unused, These are the parity bits. This key is unused, 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 last bit is unused. Okay. So this comes to the binary key like this. Now we want to create 16 subkeys, each of which is 48 bits long. So 64-bit key is permitted according to the following table PC1. Okay. First entry is 57. This means the 57-bit here. 57th bit of the original key becomes the first bit of the permuted key, K plus. This is K plus. So look at 54-bit here, permute it here to the first bit. Like that you apply this operation and we get permuted key. Okay. 56-bit permutation. Okay. I'm not worrying about the parity bits at the moment. Okay, 56-bit parity. Now you do from this master key of 56-bit key, I'm going to generate 16 keys, round keys. So split the key into left and right half. So C0 and D0, K plus we are dividing into two portions. Okay. So C0 and D0. So you can see here this master key we divided into two parts, C0 and D0. Okay. Then from the permitted key we get C0, D0, and then you see the rotations which I mentioned to you. I is equal to, as you can see that 1 2 9 16. There is a left shift one position, 1 2 9 16. 1 2 9 and 16. You shift by one position, or other number of left shifts are 2, except these one, these things. We now create 16 blocks, CN and DN. Okay. Each pair of blocks CN and DN is found from the previous CN minus 1, DN minus 1. We will apply this formula here. Apply this formula CI, DI, left shift and right shift, and apply KI as PC2 CI DI. Okay. Like this, we keep on doing and we arrive at original pair from C0 D0. We get C1 D1, C2 D2, C3 D3, C4 D4, C5 D5, and so on up to 11, then up to 16. Right. We may form the keys Kn by applying the following permutation to each of the connected pairs Cn and Dn. Each pair has 56 bits, but PC2 only uses 48 of these. This is our permutation choice 2. Okay. So each bit of Kn is the 14th bit of Cn and Dn. Second bit is the 17th, and so on. We apply this permutation. So from this is K1, K2, K3, all other keys we are getting 16 keys or sub keys. These are known as round keys. Okay. Now we encode the 64 block of data. First we first apply initial permutation. Remember this permutation we have to use from message bits. Apply the initial permutation, then L0 R0, then apply these formulas, and we have okay. Then expansion function. We apply the expansion function. Remember, this is expansion function where 16 bits are repeated twice. If you remember, we just saw that. Applying these things, simplifying it, and we then apply these S boxes operations, S1 of B1, S2 of B2, S3 of B3, and so on. As you know, what are these things? I've shown you. 6-bit to 4-bit, 6-bit to 4-bit. Remember how we need to do? Look at this. These first two will give you row, and the middle 4 one give you column number, and that row column number is SRJ, SIJ or whatever. So you replace SRC basically. We denoted the notation SRC, row and column, and that look at the binary expansion in 4-bit. Okay, that will be the C1, C2, C3, C4 or something like that, which is the output here. 6-bit, 4-bit, and so on. So basically, finally, we switch the last two blocks and we apply inverse permutation, is here in hexadecimal format. This is this. So encryption this gives us ciphertext this. Okay. This is a detailed example. I'm sure, it's a bit lengthy, but either you can write a computer program to do all these things. So remember in this algorithm, as you can see here, so these permutations are fixed. So the key generation pattern is important thing. This permutation P is fixed. These S boxes are fixed. So these S boxes are something really interesting. Each S box has 6 input bits and 4 output bits, as you can see. Okay. So I think for later on IBM published how they choose these. Each row of an S box contains all numbers from 0 to 15. You can see. If two inputs in an S box to an S box differ by 1 bit, the output must differ by at least 2 bits. That's another property. If two inputs to S box differ in first 2 bits but have the same last 2 bits, output must be unequal. That's another property. This is the property of the function that we see. There are 32 pairs of inputs having a given exclusive OR. For each of these, we compute the exclusive OR of the outputs. No more than 8 of these should be the same. Okay. These are certain basic properties of these S boxes, Now I think I should say that these S boxes are fixed. So it has certain weak keys also. DS uses 16 48-bit keys generated from a master 56-bit keys, right? 64 bits if you consider also petty bits, right? So weak keys are keys that make the subkeys to be generated in more than one round, and it reduces cipher complexity. So weak keys can be avoided at key generation. There are 4 weak keys like this. Okay, they should be avoided. So how do you decrypt it? Decryption uses the same algorithm as encryption, except that the subkeys are applied in reverse order. That is a thing. Okay. One popular Unix script function, uses DES, and it also uses a salt function to avoid dictionary attack. We can talk about these things later on, but at least, in the Unix encryption system, it uses DES, This was used quite a lot. Now there are DES mode of operations: electronic codebook mode, ECB mode, cipher block chaining mode, CBC mode, and all others. In fact, ECB is the one where uh, the plain text is divided into blocks, and on each block you apply this 64-bit DES. So if output is function of previous blocks, then they fall into all other things, But let me show you block cipher encryption mode, ECB, electronic code book. Message is broken into independent blocks of block size bits, and each block encrypted separately. Encryption, decryption. You see, EK is encryption function for DES, DK is decryption function for DES, like this. So this is block cipher mode. Actually, this NBS published all these things, the how to use these ciphers. Properties of ECB: deterministic. The same data block gets encrypted the same way. This reveals patterns of data when a data block repeats. This is one thing. Okay, reordering ciphertext results in reordered plain text. Errors in one ciphertext block do not propagate. So not recommended to encrypt more than one block of data. The other mode is CBC, cipher block chaining. So next input depends on the previous block. So encryption is something like this, you see. Okay. With and with C naught is equal to IB, and MI decryption is also like this, when the picture is something like this, it is cipher block chaining. When there is a dependency among the blocks, and there are certain things like randomized encryption. Repeated text gets mapped to different encrypted data can be proven to be secure, assuming that the block cipher has desirable properties and the random IVs are used. A ciphertext block depends on all preceding plaintext blocks. The order affects decryption. Errors in one block propagate to two blocks. That is also another thing to remember. This is sequential encryption, cannot be used parallel hardware. So there are some other modifications suggested, but we are not going to discuss more about those things. So I think that's all for DES. I hope you understood the basic thing about DES, data encryption standard. So we are going to talk about advanced encryption standard in our next class. Any question if you have, you can ask. Any question? Any question? Okay, so if there are no question,
हेलो सर।
we can yes.
सर आप क्लासरूम पे जो पीपीटी रखते हैं ना उसमें वो ब्लैंक आ रही है।
वो आई थिंक आपका कुछ इश्यू होगा, ब्लैंक आनी नहीं चाहिए. वी कैन डिस्कस दैट, यू कैन जस्ट
ओके सर।
या नॉर्मली आई थिंक एक आध लोगों को प्रॉब्लम आई थी, बट देन दे वर एबल टू सी इट. एक्चुअली ब्लैंक नहीं है कोई भी स्लाइड. ठीक है.
ओके।
ओके.